Okay, so now this is the post-midsem segment of the class, and we will do some basic machine learning techniques like support vector machine, then decision tree, linear regression, and hidden Markov model, okay, which are important for AI. Now, some of these lectures will be taken by my senior PhD student, Nihar. So today's agenda is to do a little bit of prologue because no discussion on predicate calculus is complete without prologue, which is a different way of programming a computer. Then we'll start support vector machine, which is a nice intuition of maximum margin classification. So you have done perceptron, which places a hyperline between the two classes. Now that is not sufficient. Okay, the hyperplane should be placed such that its generalization ability is very high. Since there are infinite number of hyperplanes, which hyperplane should I choose? So the one which has the best generalization ability on unseen data should be chosen. And that, of course, relates to a very fundamental concept in machine learning called bias variance trade-off. Okay, so bias variance trade-off is a trade-off with respect to which classifier I should choose for classification, given a number of choices. And then I would also like to discuss the midsem answers and then close the class today. So, so we before midsem, yeah, and also in the post-midsem segment, there will be some guest lectures and also special topics just to give you a flavor of where AI is going. Okay, what are the different areas of AI? We are covering foundations so that you can appreciate those state of the art and advancements in the field of AI. Now, what we did before midsem, the week before midsem, is that we did three kinds of inferencing and predicate calculus: forward chaining, backward chaining, and resolution refutation. In forward chaining, you start with facts and reach the goal. Backward chaining, you reach the goal, come back to the facts to support the process. Resolution refutation is essentially proof by contradiction. Then we also saw how in predicate calculus, WH questions get answered. And in particular, chatgpt was shown to be excellent in answering factoid questions, WH questions, and also how and why questions. Okay. So question answering is a very important field of artificial intelligence. And the field of AI is doing extremely well in question answering these days. Then predicate calculus is a very powerful vehicle to represent knowledge. For example, if you take this particular sentence, which is complex, in every city, there is a thief who is beaten by every policeman in the city. So this is represented by this predicate calculus formula. For all x, city x implies, okay, if x is a city, then there exists a y, thief y, and lives in yx. So y is a thief and y lives in x. And for all z, policeman xz means if z is a policeman in the city x, then y has been beaten by every policeman in the city. So we also understood that this is only a form. Okay, the content of the form is decided by the meaning we assign to these predicates: city, thief, and so on. We saw that same formula. Okay, same formula. If you bleach the symbols, city, thief, etc., from their semantics. Okay, city, if it does not mean a city, but any predicate, then we also saw that this formula can very well represent another sentence of same syntax, but different meaning. In every country, there is a city which is visited by every chief minister in the country. So that particular city is the capital of the country. The same formula can represent both if you assign the meanings to these predicates and the variables and the functions. So that led us to a very interesting topic, that is interpretation and logic. Logical expressions or formulae are forms for whom contents are created through interpretation. Now, this was an interesting example. There exists a function f such that fa is equal to b, and for all x, px implies fx is equal to g x comma f hx. Now, this particular formula, which is called a second order predicate calculus formula, because here the function is quantified. Okay, so there exists a function with this property. This we have seen represents the factorial function. So if we make a is equal to 0, this is the process of interpretation. You give values to the constants first. Now, first you decide the domain. So we are deciding the domain to be non-negative integers, okay, natural numbers. So the domain, the universe from which the values are picked up are natural numbers. So assign a equal to 0 and b equal to 1. Then the property of f is that f0 is equal to 1. After that, for all x, px is a predicate. We give it the meaning that px is true if x is greater than 0. If x is greater than 0, then fx is equal to g x comma f hx. Hx is given the meaning x minus 1. Okay, and g is given the meaning x into factorial of x minus 1. Okay, so this whole function now, this whole expression now stands for the factorial function. And if we change the domain and make the domain to be a set of strings and give the meaning a is equal to b is equal to the empty string, then f of empty string is equal to empty string. And px stands for x is a non-empty string. Gmn stands for append head of m to n. And hx stands for tail of x, the rest of the string. Then the same expression, there exists f, stands for reverse function, reversing a string. So reversing a string and factorial are both represented by the same expression. Okay, so this is the power of predicate calculus formula, second order, first order logic, and interpretation gives it the meaning. Okay, so those were the important points covered in the week before midsem. Now, predicate calculus actually went along with a very powerful and elegant programming language, though it is not used now. Prolog is programming for logic. Okay, so you wanted to capture logic in Prolog. So what is the philosophy for Prolog? Programming in logic, the emphasis is on what rather than how. So how to do the computation, you leave it to the computer. Okay, as human beings, we would only like to specify what we need. Okay, the input of the problem and the output. So you know that these days the large language models are doing an extremely good job of this. Okay, you can specify what you want through an input and output, and sometimes give an example of how this input output is achieved. That is called prompting the large language model, and then the large language model is able to do this. Okay, it is able to learn and do this. So back in 80s, this is what was in the mind of AI practitioners, that we would like to give the problem in a declarative form, and just below this layer of problem definition, there is a logic machine which does the computation, and the basic machine is the hardware with microprograms, ALU, okay, and circuits and so on, which executes and opaque to me, who is interested in solving a problem, without getting bogged down by how it is done, or even on what machine it is done. Okay, we'd like to solve a problem. So then a typical Prolog program looks like this. Suppose I want to compute the length of a string. Okay, compute the length of a string. And the high-level description of this computation is the following. The length of a list, not string, the length of a list is 1 plus the length of the tail of the list. Okay, obtained by removing the first element of the list. This is an understanding of the task called computing the length of a list, the number of elements in the list. So there is a declarative description of the computation. Okay, notice that this natural language description is something we would like to capture in the program. Okay, so this is done recursively as follows. Compute length empty list is 0. Okay, this is how Prolog functions are written. Okay, compute length empty list is 0, which means the length of the empty list is 0. Compute length head bar tail. This is called the break operation. A list is broken up into two parts by this operation. A square bracket is required. Head gives the stop talking. Okay. Head gives you the first element of the list, and tail gives a sublist. Okay, the type of tail is list. Head is an element. So if you have 1, 2, 3, then head gets bound to 1, and tail gets bound to 2 and 3 in the form of a list. The lists are represented by a square bracket and the elements within them. So compute length head tail is length. This operator is called if operator. If compute length tail is tail length and length is tail length plus 1. Okay, this is exactly the expression of the computation given in natural language. The length of a list is 1, 1, plus the length of the tail of the list, compute length tail, obtained by removing the first element of the list. How do remove the first element? By this operation. Okay, head bar tail. Any list can be broken up this way. So the way it operates is that if you want to compute the length of 1, 2, 3, okay, then this first predicate will fail because 1, 2, 3 is not an empty list. Okay, then what will happen is that these variables inside the program will get bound. Head will get bound to 1, tail will get bound to the list 2, 3. And length will be the variable which will store the length of 1, 2, 3. Then compute length will operate on the smaller list 2, 3. And tail length will store the length of 2, 3. When you go to 2, 3, then again this whole function will be called recursively. 2, 3 is not an empty list. So 2, 3 will be broken up into 2 and the list 3. Then the computation will come here. Tail is now the list 3, list, not the element 3. Okay, list 3. So here again, the function will be called recursively. 3 will get bound to head and tail will get bound to empty list. Now this predicate will be satisfied and it will return 0. Okay, so it is going bottom up. Now from the tail, 0 will come. Before that, we have already started a computation. This is in the stack for computing the length of the list 3. So computing the length of the list 3 will be 1 plus 0. And then 2, 3 will be 1 plus 1 plus 0. And then 1 plus 2 plus 3 will be 1 plus 1 plus 0. 1 plus 1 plus 1 plus 0. And this computation will be over by returning the length to be 3. That length will be obtained in length here. Okay, and this is the boundary condition. So Prolog actually is founded on recursive computation. Okay, the whole system is built on recursive computation. Okay, so some fundamentals are the following. First, Prolog was inspired by natural language and logic. How to capture logic in natural language. So John likes Mary is represented by a predicate like John, Mary. Names of relationships and objects must begin with a lowercase letter. Relationship is written first, typically the predicate of the sentence, and objects are written separated by commas and are enclosed by a pair of round brackets. As you can see here. Like John, Mary, like is the relationship, the verb. The full stop character must come at the end of the fact. There should be a full stop here. Okay. Then more facts are expressed like this. Gold is valuable, valuable gold. John owns gold, owns John gold. John is the father of Mary, father John Mary. John gives the book to Mary, gives John book Mary. This is how the facts are created. Now, Prolog has been used a lot in intelligent question answering or intelligent retrieval from databases. Questions are based on facts and they're answered by matching. Two facts match if their predicates are same, spelled in the same way, and the arguments each are same. If match, the Prolog answers yes, otherwise no. No does not mean falsity. No essentially means that from the given facts and rules, I cannot prove what you want me to prove. Okay, false in Prolog means not provable. Okay, so Prolog does what is called theorem proving. When a question is asked, Prolog tries to match transitively. When no match is found, the answer is no. This means not provable from the given facts. Okay, the variables are another building blocks of Prolog. They always begin with a capital letter. So likes John X. This question mark here, okay, is a prompt in the Prolog interface. Likes John X, does John like X? So this will be answered by matching a fact. Let's say John likes cricket. Then X will match cricket and the answer will come. X will get bound to cricket. Or you can say likes John something where capital S indicates it is a variable. Small letter means constant. But not likes John something. Here John is constant. Something also is a constant. So these things need to be remembered when writing Prolog programs. So suppose we are given these facts, likes John flowers, likes John Mary, likes Paul Mary. Now we ask a question to the Prolog interface, likes John X. What are the things that John likes? So answer is X is equal to flower. It is coming from matching this first fact. And then if you give a semicolon, it prompts the Prolog interface for more answers. Now X will also be bound to Mary and two answers will come, flowers and Mary. After that, if you again place semicolon, it will answer no. There is nothing more John likes as far as the facts are given, as far as what is given. Conjunction, use comma and pronounce this as and. So suppose you're given these facts, likes Mary food, likes Mary tea, likes John tea, likes John Mary. So if we have this question, likes Mary X, comma, likes John X. So is there something that both Mary and John like? Yeah, that is the meaning of this these two expressions linked by the comma. Comma is conjunction. So is anything liked by Mary also liked by John? So if you consult the facts here, then you can see that John likes tea, Mary likes tea. So tea is the common answer. So the way this will proceed is that there are two goals to be satisfied. Likes Mary X and then likes John X. So there are two goals here. Okay, in trying to first satisfy the first goal, X will get bound to something and then likes John and that something will be searched for in the fact base. Okay, that is how it will proceed, but then backtracking will happen. Let's see how. We have these facts, likes Mary food, likes Mary tea, likes John tea, likes John Mary. First goal, likes Mary X. Is there something Mary likes? Yes, Mary likes food. Now X becomes food. Now the second goal is likes John food. Can this be satisfied? Likes John food is not there in the database. So this will fail. Okay. Once this fails, then this arrow will move downward to see is there some other value of X which Mary likes. So X is equal to food and likes John food will fail. So likes John food has failed. Second goal fails, return to the marked place and try to resatisfy the first goal. So now what will happen is that X will get bound to T, likes Mary T. Okay. So X likes Mary T. Now likes John T. So X is T equal to T. Likes John T gets also satisfied. So both the goals are satisfied. Now the answer will come out as X equal to T. Okay. So this fact of failing on the satisfying the first goal, but failing on the second goal led to searching for more evidences for X. This is called backtracking in Prolog. Backtracking is a very important operation in Prolog. Prolog maintains a search tree of facts and tries to do a depth first search, okay, on these facts. That's why backtracking is required. Now, facts we have been able to represent by Prolog. Rules are statements about objects and their relationships. Is Prolog powerful enough to capture rules also? So rules are in the form of if-then condition. I use an umbrella if there is rain. So you see how it is expressed. Use I umbrella. This operator, okay, this operator is called the if operator or neck operator. If occur rain, okay, use I umbrella if occur rain. Generalizations also can be captured. All men are mortal. Mortal X if man X. Okay, this operator should be read as if. An animal is a bird if it has feathers. This is a more complex statement. An animal is a bird if it has feathers. So bird X if animal X and has feather X. Okay, this is how Prolog expresses rules. So now the basic syntax of Prolog is there is what is called the head part and then a body part. So naturally this operator is called the neck because between head and body, the linkage is through the neck, right? Neck. So that's why this operator is also called neck. And it is also read as if. For example, likes John X if likes X cricket. So John likes somebody if that somebody likes cricket. But this is for all quantified. Huh? John likes all and only those who like cricket. John likes X if X likes cricket. John likes anyone who likes cricket. Rules always end with a full stop. So let us take another example. This is the definition of sister. Sister of X is Y if sister of Y is X. Okay. If X is a female, female X. Parent of X are M and F. Parent of Y are M and F. So this essentially means sister, somebody's sister is a female and they both have the same parent. Okay, that is how sister is defined. X is a sister of Y is Y if X is a female and X and Y have same parents. So question answering in presence of rules. Let's have these facts. Male Ram, male Sham, female Sita, female Gita. Parents of Sham and Sham are Gita and Ram. Parents of Sita are Gita and Ram. Okay, a kinship database is created here. Ram, Sham are males, Sita and Gita are females. Sham's parents are Gita and Ram. Sita's parents are also Gita and Ram. So based on the facts and based on the rule of what defines a sister, we would like to ask, is Sita the sister of Sham? This is called a yes-no question. Is Sita the sister of Sham? So I'm asking this question to Prolog. Sister of Sita Sham. See here, there is a question mark here. Okay. Now, what will happen is that a search in the database will begin. So female Sita is correct. Parent Sita MF. So M and F get bound to Gita and Ram. Now parents Sham, Gita and Ram. okay, succeeds. So all the conditions of sister, because you see sister of XY is satisfied by three sub-goals. Female X, parent of XMF, parent of YMF. So here X is Sita, Y is Sham. Satisfy first goal, female Sita, fine. It does not bind any variable. Parent Sita MF and M and F are variables, so they get bound to Sita, Gita and Ram. Now what remains is the third sub-goal to be satisfied. M and F have become bound to Gita and Ram. I find evidence of parent Sham, Gita, Ram in the database, and so the whole process succeeds. Okay, and the answer is yes. Is Sita the sister of Sham? Yes. That was yes, no type of question. WH type of question. Suppose I ask, whose sister is Sita? Whose sister is Sita? So here I ask this question, sister of Sita X. And I want a binding for X. I want a value for X. Again, three goals need to be satisfied. Female Sita, fine. Parent of Sita MF. And we need to find out who is that Y whose parent is the same as the parent of Sita. Okay, so parent of Sita MF, M is bound to Gita, F is bound to Ram. Parent Y, Gita and Ram. Now in the database, can I find a value for Y? Yes. Y gets bound to Sham because Sham's parents are Gita and Ram. Okay, so WH type of questions are also getting answered in the Prolog environment. Okay, both yes no questions and WH questions get answered. So rules are the statements. Now a very nice operation in Prolog is called the make and break operation. Okay, so that's very, very basic. I'll take one or two examples and then finish this discussion. So Prolog examples using making and breaking of lists. So Prolog works only with lists. That is the only data structure in Prolog. Okay, so suppose I want to increment the elements of a list to produce another list. So if I am given 1, 2, 3, produce 2, 3, 4. So I write this expression here. Increment by 1 of empty list is empty list. Increment by 1 of a list can be found as follows. You take the first list and break it into two parts, H1 and T1. Okay, and obtain the result in the second list, which is the second argument of incrementing by 1. So the first element is H1, the rest of the list is T1. And the result will come in H2 and T2. How? In this way. H2 is H1 plus 1 and increment 1 is T1, T2. So what is happening? What is happening is that I have broken the input list into two parts, head and tail. Obtain the head of a new list by incrementing the head of the first list and applied the function recursively to the tail of the first input list to obtain the tail of the output list. So increment 1, T1, T2. Okay. Then appending two lists is again a basic operation in AI structures. So append 1 empty list with L gives me the same list L. Then append 1 for the input list. There are two lists actually, L1 and L2. And the third argument will obtain the result by appending first list and second list. So you have to start with breaking the list. Okay, so the input list is broken in two parts, H and L1. Fine. Then you see what is happening here. The result list will contain the head of the first list. Okay, the result list. So these two H are same. And then L1, which is the tail of the first list, and L2, which is the second list, you just run append on L1 and L2 and obtain L3. Okay, you don't have to do anything for the head of the L3 because the head is borrowed from the first list. Okay, so this breaking operation, head and tail, is absolutely basic to Prolog. Prolog works with list. List have to be all the time broken up into two parts, head and tail. Reversing a list. Reversing of the empty list is empty list. And then reverse, you take the input list, break it into two parts, H and T, and take L, which will keep the result. So reverse is called on T and L, and append L1 to H and the list H and L. Okay, so you have the head of the head of the input list, the tail of the input list, and L1 contains the reverse of the tail here. Okay, that's how this reversing will happen by calling append list. Similarly, you can remove duplicates from the list, and then member. Member is a very basic operation. So member is very elegantly written. You can see this. So you're asking if X is if an element is a member of a list. So first we are asserting that X is member of any list for which the head is X. Okay. Otherwise, X should be member of the tail of the list. So this is how it is expressed. So I do not care what is the head. The tail should contain the member. So either X is the head of the list or X is the member of the tail. Okay, this is how it is expressed. And you see the breakage. The breakage is here. The underscore indicates I don't care what the list, what this is. So here I don't care what the tail is, as long as X is the head of the list. And here I don't care what the head is, as long as X is a member of the tail of the list. Okay, so these constructs are very nice. Okay, it's a totally different approach to programming. I seriously encourage you to look at these constructs which are there in the slides and run your own Prolog programs also. You can do interunion, you can do intersection, you can compute XOR, all recursively by breaking the list into two parts. Okay, so very quickly, okay, now Prolog programs are close to natural language. So to find out if E is a member of the list L, this is how you recursively write a Prolog program. And if you want to do this in C program, then you see you will need a loop here for I equal to 0, I less than length of L, I plus plus. If E is AI, break. E has been found. Otherwise, if I is less than length L, success, else failure. So this kind of looping over the list is not very natural to our thinking. What we are saying here is that we are giving a process. Take the element, compare with every element. In Prolog, we are simply saying if the element is same as the head of the list, it is there, or it should be in the tail of the list. That's all. No, very different from saying compare each element in the list. Okay, you see this difference, it's a subtle difference and very different approach to programming. Okay, so let me start a very important topic in about 5 minutes. Okay, from tomorrow, this will be detailed out a little more. So support vector machines, they learned a linear separator for separating instances belonging to two different classes. This is how it does it. Okay, it places lines exactly like perceptron. Places lines between the two classes, the blue class and the red class. The only thing it does is that it chooses a linear separator which has the maximum margin. Okay, so out of these lines, which one should I do? All of them are achieving the purpose. I will choose the one which has the maximum margin of separation on the two sides. So on the two sides means what? You have to take the boundary points of the cluster of the class number 1. So those boundary points are called support vectors. Okay. So the boundary points are these and these. And here on the red class, the boundary points are this and this. Now, this hyperplane is chosen because it is in the middle of the two boundary lines going over the support vectors. Okay. So there are infinite number of lines which will satisfy separability, but I'll choose the one which gives me the maximum distance counted from both sides of the positive class and the negative class. So this is called a maximum margin separator. Okay. And why do we choose a maximum margin separator? We intuitively hope that a maximum margin separator will be successful in generalizing best for new instances. So suppose my separator was this. Okay. If my separator was this, in future, if a point comes here, this will be correctly classified. If a point comes here, this will also be correctly classified. Okay. So when you see the unseen points, this maximum margin classifier has the highest probability of best generalization. This can be proved theoretically. Maximum margin classifier has the best generalization performance. So let's see how we do it. It requires some simple coordinate geometry. So a hyperplane which separates the two classes is expressed by this equation. W1 x1 plus W2 x2 plus W1 xn plus W0 is equal to 0, which can also be written in the vector form as W transpose, the weight vector, dot x, the input vector, plus W0 is equal to 0. Now, if you remember from your coordinate geometry, the vector W, okay, of Wt dot x is perpendicular to lines of the form Wt dot x plus W0 equal to 0. Okay, it is perpendicular to this line. W is perpendicular to this line. The learning task in SVM is to determine the optimal values of the parameters representing the linear separator with the maximum margin. Okay, let's see how this is achieved. So, so we go by the definition of separator. The classes of the points belonging to one class are on one side of the hyperplane. The points belonging to the other class are on the other side of the hyperplane. Okay, that basic definition remains. Okay. So how do we see the margin width? Now the points are given in the form of x1, y1, x2, y2, x and y, and so on for these two clusters. Okay. And for each of these points, there is a label. The points are x1, x2, xn, and so on. The labels are y's. Okay. So for some mathematical convenience in support vector machines, we deal with the labels +1 and -1. Okay, we'll see very soon why it is so. So yi belonging to +1 and -1 is its corresponding true class level. So let's say these belong to people whose loan has been sanctioned, and these red points belong to people whose loan has not been sanctioned. The x1 vector is for the first loan applicant, x2 vector is for the second loan applicant, and so on. Let's say the first loan applicant's loan was successful, application was successful, then y1 will be equal to +1. Let's say for x2 it was not successful, then y2 will be equal to -1. Okay, this is how the data points are given. Let me stop here. Okay, that's because I want to discuss a few points about the midsem. So, it will be shown how this margin is computed and how it is satisfied. Okay. Okay. So my impression after looking at your papers is that it's okay. Okay. Not, I'll say, superlative excellent. Okay. Types. So we'll bring out the actual marks soon. So let me go to the subjective part. Subjective part was not satisfactory. Okay. Which had 15 marks. So let me start with the last question. And you had your space constraint. Okay. You had to accommodate the answer in that space, which could be done. Prove in the Hilbert system of propositional calculus the commutativity of AND operation. One direction is enough. You can use only axioms, modus ponens, and any meta theorem. If you need a theorem, you have to prove it. So meta theorem means you need the deduction theorem. Okay. So we want to prove P and Q implies Q and P. You have to first convert it into Hilbert propositional calculus form. P and Q is in the form P implies Q implies F implies F. That should imply Q implies P implies F implies F. Now apply deduction theorem. This actually wants you to prove P implies Q implies F, comma, Q implies P implies F derives F by deduction theorem. Okay. Now, Q implies P implies F derives P implies Q implies F. Okay. Q implies P implies F derives P implies Q implies F, since Q implies P implies F and P and Q derive F. This is a sub-theorem. Okay. So Q and Q implies P implies F gives you P implies F, and P implies F gives you F. Okay. So Q implies P implies F derives P implies Q implies F. Now, if you use this in A, then F gets proved. Okay, because Q implies P implies F derives P implies Q implies F. Apply modus ponens on this, and F gets derived. Okay, so this is how it is proved in one direction, and you get 4 marks. I'm not sure I saw many right answers there. Then this question was this. In perceptron training, if it ever happens that a weight vector reappears, then the function attempted to be trained on the perceptron must be linearly non-separable. Okay, you have to prove necessarily making use of the GWN function defined in the class. There can be different ways of proving it, but your hands were tied. You had to make use of GWN. I wanted to make sure that you understand the property and the importance of the GWN function. Okay. Now GWN, you remember, was defined as Wn.W star divided by mod of Wn. Now you can create GWN only if the function is linearly separable. Otherwise, W star does not exist. So the moment you use GWN, you're assuming that the function is linearly separable. You're using W star. Now Wn.W star is Wn plus 1 plus x fail dot W star. Wn.n minus 1 dot W star plus x fail dot W star. Now x fail dot W star is strictly positive. Okay, if you have function W star exists, and W star will multiply every vector giving a positive value. So this means that Wn dot W star must be strictly greater than Wn minus 1 dot W star. So as the iteration proceeds, then Wn and Wn minus 1 and Wn minus 2 and Wn minus 3, all of them have to be different. Otherwise, they cannot be strictly bigger because W star is same. This means Wn's are strictly increasing. So if all assumptions are correct, then no weight can repeat. Since, however, weight has repeated, the assumption W star existing is wrong. No such W star can exist. This means that the function is not linearly separable. You had to prove using GWN, no other proof will be accepted. And you see, it is just 2-3 lines proof. and the space is sufficient. Okay. Then you had to prove something which I have repeatedly told in the class. Prove rigorously that the number of threshold functions of m variables is ordered 2 to the power m square. What we proved in the class is that Rn comma d is 2 into I equal to 0 to d minus 1 Ci n minus 1. So the number of regions created by n hyperplanes passing through origin in the d-dimensional space is 2 into I is equal to 0 to d minus 1 Ci n minus 1. So let's see. For our case, n is equal to 2 to the power m. If there are m input variables, okay, then 2 to the power m points there, right? And d is equal to m plus 1. So bias is absorbed as an additional weight. Hence, the required quantity is, we are asking in the m plus 1 dimension, how many regions will be produced by 2 to the power m hyperplanes? Okay, so that quantity will be 2 into I equal to 0 to m plus 1 minus 1 Ci to m minus 1, 2 to the power m minus 1. I hope it is visible on the screen. Okay, so then m plus 1 minus 1 is m, 2 into I is equal to 0 to m Ci 2 to the power m minus 1. And 2 to the power m minus 1 can be written as 2 to the power m. 2 to the power m is large compared to 1. Now this is less than or equal to 2 to the power m to the power I. We are making use of the inequality. N choose r is less than or equal to n to the power r. So if you do that, then we have 2 into I is equal to 0 to m 2 to the power m into I, which is a GP series. Okay, GP series with common ratio of 2 to the power m. So this is equal to 2 into 2 to the power m square minus 1 divided by 2 to the power m minus 1, neglect minus 1, which is equal to 2 to the power m square minus m plus 1 order 2 to the power m square. So this should not have taken you too much time if you are making use of this inequality and also the GP series expansion. Okay. However, I don't think these 15 marks is whatever sampling I did. I don't think anybody was getting full 15 on all the three. Okay, this was the subjective part of the test. And your space was constrained. You are not allowed to write, a big history, just clean, crisp answer. Now let's go to the objective type questions. Here, you have to get all and only those answers, otherwise you get -1 or 1.5. So Sear's Chinese room experiment dash the Turing test. Fill in the gap with correct options. Reinforces, challenges, is irrelevant to none of the above. The answer is B, challenges. Okay, even if an entity can fool, okay, a third interrogator, a third entity, interrogator saying that I am a man, not a machine. Even then, it is not a sufficient proof for intelligence because of the Chinese room experiment of Searle, where we saw that a man can simply mimic a program, okay, which has an exhaustive rule of Chinese speaking. And the man himself says that I do not know any Chinese, but I am able to pose as a Chinese. Okay, so it actually challenges the Turing test. For the sentence foxes, foxes, fox, fox, foxes. So the meaning of this sentence is that those foxes which other foxes deceive, fox is the word meaning of deceive, in turn deceive foxes. So you can see here, foxes that other foxes deceive a third set of foxes. So the main verb is fox4. Okay. So in the 8 puzzle, we have this goal state 1, 2, 3, 4, 5, 6, 7, 8 and blank. Row major order. So 1, 2, 3, 4, 5, 6, 7, 8 and then blank. So here the answer is B. Okay, I sent a correction. saying that the answer is only B. And the property it uses is that if the goal state has even number of inversions, where inversion means a larger number is before a smaller number in the row major order. Now in the goal state, you can see 0 inversion, okay, which has even parity. So in the first option, 1, 2, 4, 3, 5, 6, 7, 8, B. In the first option, there are how many inversions? Larger number has 1 inversion, and B has 2 inversions, even parity, and 3 has 3 inversions. Okay, in 3 you can see it is 3, 2, 2, 1, and 3, 1. There are 3 inversions. So only B is the answer. B is the answer. The goal state is reachable only from B. This has even number of inversions. Okay, so that was for this. Now in this search graph, 1, 3, 10, 5, 5, 4, 6, 2, 3, 7. The heuristic values are HA equal to 13, HB equal to 16, HC equal to 18, HD equal to 8, HE equal to 12, HF equal to 1000, HG equal to 0. Okay, here you see the heuristic values are always overestimating by 5. Okay, overestimating the H star value by 5. Then we have proved a theorem in the class that the found path need not have a cost more than the optimal plus 5. So the answer therefore is A, at most 14. Okay, as proven in the class. Now this I think some of you have questions here. So you see the heuristic values are everywhere 0. And if 3 has a heuristic value which is 3, okay, if this 3 has a heuristic value which is 3, then the expansion sequence will be the following. Okay, so you'll be forced to first expand 1 and 2, and then 4 will come. Okay, 1 and 2 have to come before 3 because the heuristic value of 3 is 3. And therefore F value will be much higher than 1 and 2. So before expanding 1 and 2, you'll not be able to get 3. And therefore 4 has come into the open list. And after that 4 will get expanded because F value is still less than that of 3. Now, when 3 gets expanded after these, the parent pointer of 4 will get changed to 3 from 2. Though this situation is possible only if H3 is H3 is 3. Okay, so some of you have given the answer as 4 and 5. You have marked 3, 4, 5, all of them. Okay, because it doesn't matter whether 4 has a value of 2 and 5 has a value of 2. It doesn't matter. I'll consider that answer, but a clean proper answer is A. Okay, because 3 cannot come into the open list before 1 and 2. So if you have questions, etc., just send mails. Okay, we'll surely consider this. Then consider the proof of the theorem. Phi implies P in Hilbert propositional calculus, where phi is the syntactic false symbol. Phi, comma P, comma F implies F using deduction theorem. So phi implies P is broken up into 2 parts. Phi, comma P implies phi derives phi. Okay, so phi derives XYZ, phi derives XYZ and PQR, and from there you would derive P. Therefore, phi implies P is a theorem. So my question was, what are XYZ and PQR? So the answer is C, material transfer to the right of derivation, application of axiom 3, and application of modus ponens. Okay, so PQR, XYZ becomes P implies F implies F, and PQR is P implies F implies F implies P. So axiom 3 has to be used and modus ponens has to be used. So only C satisfies that answer. I think most of you got that. Oh, it's already time. So I think I'll stop here. Okay, rest of the answers you can look at the model answer. So tomorrow's support vector mention will be covered. And if you have any questions, please send a mail to me.